A massless cable of diameter 2.54 centimeters or 1 inch is tied horizontally between two trees 18 meters apart. The figure is shown here. A tightrope walker with mass 39 kilograms stands at the center of the cable. The cable stretches and makes an angle of 1.5 degrees with the horizontal. The Young's modulus is defined as the ratio of stress to strain, where stress is the force applied per unit area, or pressure, and strain is the fractional change in length, change in L divided by the original length L. What is the cable's Young's modulus? So let's start by defining stress and strain. So stress is simply the tension force divided by the area, since the tension is the force that the person is acting on the rope right now, in this case. An area is simply the cross-sectional area of the cable. Strain is the fractional change in L divided by L, the original length. So let's start by figuring out tension, what tension is. So if I draw a free body diagram of the person, let's say that this is the person, there is a tension force. I can't draw straight right now. So there is a tension force pulling on both sides of the person from the cable. And then there is the force of gravity pulling it down, mg. And these tension forces can each be separated into their individual horizontal and vertical components. So the horizontal component is simply t cosine theta. Hold on, I'm going to redraw this part. And this is pointing down, that's mg. Here is the angle theta, which you can get using alternate interior angles. And so this is t cosine theta, and this is t sine theta. You can use some basic trigonometry to figure this out. And now we can write our equations. So we know that both of the vertical tension forces acting together are working to prevent gravity from accelerating the person down. So equals ma equals 0. Since there is no acceleration, this whole right side of the equation is 0. So 2t sine theta is equal to mg. And now we can just simply solve for t, which is mg divided by 2 sine theta. And now we just need to plug everything in. The mass of 39 kilograms times 9.8 meters per second squared divided by 2 times the sine of 1.5 degrees. And if you evaluate this, tension is about 7,300 newtons in the rope. So we have figured out tension for now. 7,300 newtons. So that's tension. Let's get rid of everyone. Now we need to figure out area. Now, if you think about it, we have this sort of circular cable. The cable is circular. So if you take the cross-section of it, the cross-section will be a circle. And the area of the circle is pi r squared. And we're given the diameter, and the radius is simply the diameter divided by 2, which is 2.54 centimeters divided by 2, which is 1.27 centimeters. And now we can just plug everything in, pi r squared. I'm going to convert this to meters. 1.27 centimeters is 1.27 times 10 to the negative 2 second power meters. And we're going to square that. And that is simply area, the area of each little cross-section. So area is equal to pi times 1.27 times 10 to the negative second power squared, square meters. So the tension divided by the area is simply this over this. 7,300 newtons over what we just calculated. Now let's move on to the change in L. So we already know that L is equal to 18 meters is given in the problem. So now let's figure out the change in L. So to figure this out, start by drawing a diagram that is very similar to the one that is provided. Here are the cables, the middle is your person, and let's say that this horizontal line, or the horizontal, is simply 18 meters. That's the distance between the two trees. Now, when they form an angle of 1.5 degrees, they're bending the cables, and this actually makes it longer. As you can see, you can divide these two sections into congruent right triangles. So let's erase this. You can separate them into two 9-meter sections, since the person is standing directly in the center. And now, since these are both right triangles, this is perpendicular, the vertical line is perpendicular to the horizontal. You can use some trigonometry to calculate the length of the third side here. So if you remember, you can say that the cosine of 1.5 is equal to the adjacent divided by the hypotenuse. So the hypotenuse is simply 9 divided by cosine of 1.5. And there's 2 of them, so we actually have to multiply it by 2. But we'll get to that in a moment. So the change in L, or the fractional change in length, is simply equal to the new length minus the original net length. So from what we found earlier, the new length is 2 of these x's, where each x is 9 divided by cosine of 1.5. So 9 divided by cosine of 1.5 times 2, which is 18 divided by cosine of 1.5. So we can say that the change in L is equal to 18 divided by cosine of 1.5 minus the original length of 18 meters. And now we can factor out the 18. Just 18 times 1 over cosine of 1.5 minus 1. So there's that. And that is change in L. So that is change in L and not L. So change in L is equal to 18 is 1 over cosine of 1.5 minus 1. And now you might see that we will be able to simplify it, because the ratio change in L over L simply cancels out both of the 18s. So strain, what you get for strain is simply 1 over cosine of 1.5 minus 1. Sorry, minus 1 is outside. So that's strain. And stress, if you remember earlier, was this value over here. That's stress. So now all we need to do is put everything together. So it's stress divided by strain. So if we just plug everything in, we get tension force divided by the area all divided by the strain. This is looking quite messy right now. So I'm gonna erase some stuff. And then now we just need to kind of simplify this. So this simply becomes 7,300. I should probably say that it's equal to Young's modulus. Represent Young's modulus as y. To 7,300 divided by times 1 over cosine of 1.5 minus 1 times 1.27 times 10 to the negative second power squared. And now all we need to do is just plug this into a calculator. You should get that this is about 4.20 times 10 to the 10. And I actually don't know the unit yet, so I'm going to go and figure out the unit. So remember, stress over strain. So this becomes TL over a change in L. So this gives you Newton meters divided by meters cubed, which gives you Newton over meter squared. So that's our unit. So the Young's modulus for this cable is 4.20 times 10 to the 10th power newtons per square meter. And that is how you would solve this problem here.